Okay, so here's what you all did. You took a rubber stopper, you swung it around over your head, and there's certain key assumptions that you make. On the beginning part of the data analysis, you assumed that the weight of whatever was hanging down was what was creating the centripetal force, okay? So on trials 1 through 4, you should have a graph that looks something like this, where you've got velocity here, force here, and this should look something like this, okay? Now, understand why. It's because centripetal force equals mv squared over r. Mathematically, you kept the mass of the stopper a constant. You kept the radius a constant. If you wanted to, you could actually find that numeric constant. You could take that mass of that stopper, divide it by 0.8 meters, and get a number, okay? And then it just becomes, oh, that's just a constant of proportionality, where you have set FC equals some constant times v squared. That's it, okay? That's why it's a quadratic relationship. So make sure when you answer question number 4 that you have mentioned all 4 variables: centripetal force, mass of the stopper, velocity, and radius. So when you answer 4, 8, and 12, you want to make sure that you have mentioned all 4 variables in that equation. If you haven't, you have done something horribly wrong, okay? And if you're not sure if you have, give it to someone else and go, hey, did I talk about all 4 variables? If they go, no, then stop, don't hand it in. Now, the second set of data, when you look at centripetal force equaling mv squared over r, so this one you kept the centripetal force the same, and you kept the mass of the stopper the same. So if you wanted to, you could take that centripetal force divided by the mass and then get v squared over r. So this would be your constant, okay? This is what it would look like. This would be a constant. Then if you wanted to, you could multiply by r, and then you would have, oh, some constant times r equals v squared. Then if you wanted to isolate v, you'd have v equals the square root of kr. Mathematically, that's what you end up with, okay? So that's why this graph should look something like this, okay? In an ideal world, that would be a square root function, okay? The third one, which you all seem to have struggled with data, this is the only one that's an inverse relationship. So again, you got centripetal force the same, you have the radius the same. So you could write that as centripetal force times r equaling mv squared. Okay? That's what you got. So this gets a little bit wonky because of the fact that with this one, you're going to graph radius here and you're going to graph velocity here. So if you isolate that velocity, number one, it's going to be an inverse relationship because you're going to divide by mass, but then you got to take the square root of it. So it's actually an inverse square root function, which gets really kind of weird mathematically. But that third graph should look something like this. Okay? Now, if you have an outlier, which sounds like some of you might, then just realize what that graph should look like. So I guarantee you, if you have like a point up here, don't do this and go, oh, there, we have a mustache. No. Okay? Smooth out the curve, all right? Just know what that should look like.
I feel like ours is about to smooth out to the wrong direction. Like it's funky.
The one with the mass is usually the most home run of all of them. The one that usually gets weird is the one where you change the radius.
No, I think the one where we change the radius adds up.
That's the most normal one.
Yeah, the one where we change the radius is the most normal
one. The third one are usually home runs.
But for us, it was like the 10th, like our 10th day, trial was the worst.
No. It was 11 where it's funky, because...
Okay.
I don't know. I have two where it's the same speed.
You have
I
what?
don't even know what happened.
It's because they're the same conditions.
I mean,
No, well, I have two different masses
that's
though.
my first graph. I don't even know.
I haven't even done this inside.
No, you
Okay, anyway,
I do.
you will have jacked up data.
Look.
So here's the story. When you get to question number 13, on 13, you're gonna see, hey, is the assumption actually valid that the weight of what's hanging down is what's creating the centripetal force? Okay, so you're just saying, hey, this is really valid. So on number 13, you're gonna go to trial number 4. And trial number 4, everybody used 0.4 kilograms, which weighs 3.92 newtons. So the assumption is that what's creating that inward force as this thing goes around is that 3.92 newtons. So then you actually spun it around, and then you're going to compare that using mv squared over r. So you're going to go to trial number 4. You're going to find the mass of the stopper, whatever velocity that you all have, a radius of 0.8,
I was lost.
and you're going to calculate the centripetal force that way. Do not put 0.4 kilograms in there for that mass, okay? That is not the mass of what's hanging down. That is the mass of the stopper, because that's what's undergoing
That's not
centripetal acceleration. So then, basically, like on trial number 4, you're going to take 3.92 newtons minus what you get from here, mv squared over r, divide that by 3.92 times 100. So you can do that for trials 4, 8, and 12. When you get to question number 15, and you're going to talk about the Earth moving around our star, obviously there has to be some amount of centripetal force between the Earth and the Sun. If there wasn't, we wouldn't orbit the Sun. Okay, conveniently, we live in a universe where there's gravity. Because if we didn't live in a universe without gravity, we wouldn't be here having this discussion. So, what I would recommend is that you go straight to mass 4 pi squared r over t squared. You can go through and find the velocity using 2 pi r over t. And then you can plug that into mv squared over r. You can do this. It's an added step, okay? Because you have to calculate the velocity separately, and then you have to plug that into the mv squared over r. This one, you just do it at just all in one step, okay? It just makes it easier. So when you get to a problem like number 15, and we're gonna get more and more into this, when you convert that year into seconds, do not round that number. You keep all of the seconds, okay? 1 year is not a measured value. So when you convert 1 year into seconds, don't round that number. Bowen?
Okay. I'm pretty good about not rounding.
Okay.
That's my one.
Now,
One
when you
skill.
get to number 16, by the way, that answer to number
close to
15
that
should be a
shot.
really, really, really big number. Like, really big.
Of all the people you should tell not to round, it should be Round Sean.
Yeah. Okay, now, here's the next question when you get to number 16. Now you're talking about someone standing on the surface of the Earth at the equator as they go around, okay? And you're going to try and find the amount of centripetal force needed to keep this person on there. So, here's kind of the weird thing. Because our Earth is spinning, which is a good thing, okay? If the Earth didn't spin, as a matter of fact, it's been estimated that if the Earth was spinning like 10% faster than what it is, that we would have such violent winds at the equator that basically the storms would be so severe that nobody could really live anywhere near the equator because we'd be spinning so fast. The Coriolis effect would be on steroids. If we were spinning 10% slower, that would also be a horrible thing because the days would be longer, the nights would be longer, and you'd get more extreme temperature changes. And so that would also tend to wreck our weather systems. So we orbit just the right distance, we have just the right spin, and we're tilted on our axis. So because of the fact that you're spinning, and we'll talk about this today, as you come around, your body actually wants to travel in a straight line. So if you're at the equator, because of the fact that you're spinning and you want to go flying off, you actually weigh a little bit less at the equator because of the fact that you're spinning and you want to travel in a straight line than you do at the poles, because of the fact that it's just like me spinning this rubber stopper around, okay, right? It always wants to go flying off in a straight line. So right now, you all don't want to sit here. Your body wants to make you go in a straight line, but conveniently, you've got a gravitational field. So on number 16, what are you going to use for the period? 365 days or 24 hours?
24 hours.
24 hours because the Earth is spinning on its axis. So what you should see, and this is the good thing, is that your answer to number 16 should be exponentially less than what that person weighs. Okay? So that person weighs about 700 newtons, which is the measure of the gravitational force between that person and the Earth. The amount of centripetal force that you need to keep that person on there is a lot less, okay? Which is a good thing, because if the centripetal force that you need to keep an object on the surface of the Earth is less than what it weighs, we wouldn't be here having this discussion,
You gotta.
okay? Because gravity is the only thing holding us on. And if you needed more centripetal force than what gravity could provide, you're off to the races.
Preston.
So, what?
He may or may not gotten 1.74 times 10 to the 28th.
For what answer?
That one.
On 16?
Apparently.
What did you get? Preston, what did you get?
1.774 times 10 to the 28.
16?
What numbers did you use?
Oh, I used math for. I screwed up.
Yeah.
He used the mass.
Wow. That ranks up there with Danny's calculation of acceleration due to gravity. Remind me to work in Danny's falling safe acceleration.
Okay.
Oh,
yeah.
yeah.
Oh
Okay.
yes.
Remind us to work that.
So write it on a whiteboard somewhere.
The Mach 2 acceleration.
Don't forget Mach 2 acceleration. I think
possible.
gravity.
I think Danny
Here's
has
all I
been
need
beat.
to write. Danny G. I don't know exactly what that means.
We should have a list, the biggest mess ups, and
Oh,
have
yeah.
the top 3. It goes Preston, Danny, and then me.
I thought it was Cohen. I forgot
Is
what
that
it
just the
was.
wall of shame?
Yeah.
Preston, what was that answer?
Nah.
No, what was
I
the answer?
fixed it. I fixed it.
1.74 times 10 to the 28th.
Mittens.
Wow. Wait, am I supposed to get like 2.36 newtons?
You're
Yeah,
supposed
it's
to have
gonna- yeah,
less than
Yes.
supposed to have less than 70
Is
kilograms.
that
No, less than 700
Oh,
meters.
that's seconds.
no? Like how many? What
Yeah.
seconds is that?
So
64
what he
hours.
essentially solved for would be like if the Earth was standing
I
on
was
the Earth
really
as it
confused on how
spun.
to actually solve that.
Yeah, that's how much force it would take to keep the Earth on the Earth as
Spinning.
the Earth spins.
Yeah, that's good to know.
Noted.
Yeah,
Noted.
yeah, that's a unique way of putting it. Yes. Okay. All right. Anything else?
Actually.
Oh yes, like I'll
Very
just
hard, I would say.
You got
For every
it.
body diagram, do we have to put like force gravity like downward?
Does it force gravity? Does force gravity
Preston,
go down?
how long have you been my student?
About 10 weeks.
Yeah. What? From the very first day you were in this class and we did the spring lab. What did we talk about? What force did we talk about?
Gravity.
It's pretty.
Which direction did that force act?
But like I didn't know if I needed to put it like for this.
Go it.
Have you done any of these?
What does the opening line say? Preston, what does the opening line say
Show
on
all
17?
forces.
Show how many forces?
All.
All the forces. Think gravity might be one of the forces? Think you might want to include that one? Let's go with yes. Make sure on 17 that I see the scale and you drew it with a ruler. Okay? It's not a freehand sketch.
No.
Draw it with a ruler.
Oh,
Mucks.
I just started freehanding it as you said that.
Oh, my bad. I didn't put that in the instructions.
Well, I didn't read the instructions. I just assumed.
Really? There's a shock.
Can you put no scale for the scale that was used?
I can put no points on it. So yes, you can. But there's your trade-off. Here's your grading scale.
What if the scale is just?
Shut it.
Do you measure our scales to make sure that it's accurate?
Sometimes I do.
Oh.
Like, yeah.
Hmm.
Mr. Brookman, on that one,
What do you
I
expect him to say?
already rounded the period of the Earth on that. It's on the previous assignment. So,
What do you mean round? The
Yesterday I told you not to do that.
do you?
Round Sean
Yes.
coming in the opposite
Yes.
clutch.
Oh.
What does rounding the period of the Earth mean? I know what the period of the Earth is, but
Like, if you take 1 year, okay, and you go 1 year is 365 days, technically 365.25, and then 1 day is 24 hours, and then 1 hour is 3,600 seconds. What I'm telling you is when you do this math, keep all of those digits. Don't round that
I kept
out.
most of them.
Okay?
He kept most of them.
I was 16.
That's a good
I
start.
think it'll come out to exactly 6 meters per second. If I
Here,
do
give me
keep
your
it.
16.
What?
What?
No, like my answer, at the end, my answer will come out to exactly 6 or something. Yeah, at the
Rabbit.
end. At the end.
It's a rabbit.
Okay, now my.
Wait, what question was that on?
Number 7.
3186452
Are you
zeros.
sure that
I got 5.8 times 10 to the 24th.
that's supposed to be a 3?
Is that right?
Huh?
5.8 times 10 to the 24th.
Whoa.
Also, this is a
What? Per meters per second? wait.
So,
Oh, I didn't put a unit, so yeah, that's a
Are
thing.
you in meters?
yeah.
Oh.
Yes, Danny, meters per
That's pretty
second.
good.
Nah, Denny, seconds per meter.
Okay, tell one stop that camera.
Uh oh.
That's not good.
Just